Welcome in this class on powertrain vibration. And the objectives of the class are to understand the concepts of vibration, mechanical vibration of systems with 1 degree of freedom, multiple degrees of freedom, and also continuous systems. And specifically, we want to learn how to develop an analytical model of the system, a mathematical model that represents the system in terms of equations, and then how to solve these equations to find the response of a system to a given excitation. This class is on vibration. Vibration is a periodic type of motion that a system has in response to some excitation. That excitation can be a harmonic force, it can be some force like an impact force, and we want to study and have tools to study and predict this response. Vibration most of the time is undesirable. Examples of cases where vibration is undesirable are vibration of a car. Say the hood of a car vibrates, and as a result, this is something unpleasant. You want to have a car that is quiet, has low sound and low vibration. Sometimes vibration, though, is very useful. An example is when music. When you have an instrument and play music, there is vibration, and that creates sound that is transferred. Voice is generated from vibration of the vocal cords. Here is my name and information about the office, my email address. A lot of communication can be done using the email address. And some information about the text. This is an old textbook by Roy Craig, and this is a pretty good book. There is a newer version from 2006, but any of the two will do the trick. There is another reference on mechanical vibration, which is optional. So the first part, as the introduction, will talk about vibration, how to perform an analysis of a system, how to model it first, and then how to create some equations that govern the performance of the system, and then solve these equations to find the response. We'll talk about then single degree of freedom systems. Single degree of freedom systems are defined, their position is defined in terms of a single variable, a single independent variable. So you just need one number to define the position of the system. And that is the degree of freedom. We'll learn how to write the equations of motion. So we'll have a model of the system that is an assembly of different elements such as springs, masses, dampers, and we'll write an equation that governs the motion of the system. So there is a relation between the excitation, the force that is applied, and the response of the system, which can be the displacement. So this could be the first part that will write these equations of motion. Once you write the equations of motion, you solve them to find the vibration of the system, find how the system responds to an excitation. And there are two types of vibration. One is free vibration, where the system is not subjected to any forces. The reason it vibrates is because it has been perturbed from equilibrium, and then it vibrates until it returns to equilibrium. So because there is no force applied, this is called free vibration. Then we have forced vibration, where a system of forces are applied and excite the system. We have different types of vibration depending on the excitation. One is harmonic excitation. Harmonic can be a sinusoidal function, a function of time such as sine of t or sine omega t. We can have periodic excitation, which is an excitation that repeats itself every certain interval. And then the last one is the general type of excitation. So this will be the first part of the class after the introduction, and it will deal again with 1 degree of freedom systems. Then we'll consider systems with many degrees of freedom. Again, in this case, we have to define the number of degrees of freedom. These are the numbers that the minimum number of variables that are required to define the position of the system in space. So you have multiple numbers, and we'll derive the equations of motion. Then again, we'll study free vibration, and then forced vibration. When we do free vibration analysis, we'll consider patterns of motion of the system that are called mode shapes. We'll examine their properties, and we'll see how to work with the equations of motion. Then for force vibration, we're going to again work with solving the equations of motion to find the response. And we'll consider different methods to do that. One is direct dynamic matrix inversion. The other is the mode superposition method and the mode acceleration methods. So this is about multi-degree of freedom systems. Then we have continuous systems. Continuous systems have actually infinite number of degrees of freedom. So there are infinite variables whose values have to be defined in order to determine the position of the system in space. In reality, every system is a continuous system, okay? Because anything that you think of, like this table, has infinite degrees of freedom. That means there are infinite number of points, and theoretically, in order to determine the position of this table in space, you have to define the positions of all these points. So infinite points, infinite degrees of freedom. In reality, everything has infinite degrees of freedom, but we can get decent approximations using either one or multiple degrees of freedom. But here we'll really consider systems with infinite degrees of freedom. These are the continuous systems, and again, we'll study first the equations of motion. We'll see how we derive the equations of motion of a continuous system, such as a beam or a plate, then free vibration, and then forced vibration. The next part is finite element analysis. Finite element analysis is a numerical method that we use to predict the behavior of a system, and we'll study how to use this approach to find the response of a system to a given excitation. In practice, very rarely we use directly the equations for continuous systems. We'll use this finite element method to find the vibration of a system. This is a very general numerical method, and this is what we'll use in practice. This is a paper that I have authored, as you can see, long time ago, that deals with the torsional vibration of a system, a propulsion system of a diesel engine. And this is a good application of what you learned in the previous chapters to a real-life problem. So you'll see if you have an engine, how it vibrates in torsion because of some excitations, either from the engine itself, from the pistons, or other sources of excitation. This is the grading policy. There'll be typically 9 homework assignments. There'll be 2 quizzes, 4 quizzes, and a take-home final exam. And this is the grade, how your grade will be derived. Homework assignments and the final exam count total 60% and the quiz is 40%. And here is the correspondence between the numerical score and your grade, your letter grade. So if your score is between 90 and 100, you get an A. If it is between 80 and 89, you get a B. Between 70 to 79 is C. And let's not discuss what will happen if you get below that. Okay? So now that we completed the syllabus of the course, let's look at the schedule. This course will be, typically will last between 13 and 14 weeks. And here is what we'll cover each week. So the first week we'll talk about the introduction and see an overview of an investigation of the dynamic performance of a system because of some excitation. Then we'll start talking about single degree of freedom systems, and the first topic is equations of motion. We'll see how to derive the equations of motion. Again, an equation of motion is an equation, a differential equation, that relates the force to the displacement of the single degree of freedom system. So it's an equation that involves derivatives of the displacement, first and second derivative plus the displacement itself. And this will take us 3 class sessions. So this will be the first week plus the first session of the second week. Then the next topic is free vibration of single degree of freedom systems. So we'll see how a system vibrates if you displace it from the initial equilibrium and then you release it and let it vibrate. This is expected to take 2 class sessions, so 1 week. Then the next topic is forced vibration, and it will take again 3 sessions. So the first 4 weeks will be spent on single degree of freedom systems. Then we'll talk about 2 degree of freedom systems, systems that are defined in terms of 2 degree of freedom systems, 2 degrees of freedom, 2 coordinates. Now, whatever we learn there is easily transferable to multi-degree of freedom systems, 3, 4, 5 degrees of freedom, and so on. Once we have, we'll continue here with 2 degree of freedom systems, equations of motion. Then we'll study free vibration, and this will take, again, 3 classes. And this is an estimate, of course, depending on how fast we're making progress. Then the next topic is forced vibration, and forced vibration is expected to take for multi-degree of freedom systems 4 class periods. And in the 10th week, we'll start talking about continuous systems. Again, a continuous system is something that has an infinite number of degrees of freedom that define any point in the system, such as a beam. A beam theoretically is determined, the position of the beam is determined based on all the points in that beam, the coordinates of all these points. Once we finish the continuous systems, during this period, then the last 2 weeks will be on finite element analysis, which is the numerical method to essentially solve the differential equations of motion of the system. So with this, let's start talking about this class with introduction. So we'll see the steps that we'll take in order to analyze a structure to find the dynamic behavior of the structure. So let's consider the first step, which is starting from an actual structure. So this could be, for example, a building. Okay, tall building. Now the first step is to simplify it. You cannot analyze everything. You cannot consider an infinite number of degrees of freedom for a 50-story building. That is not feasible. So you got to do some simplifications. So the first step is to make some assumptions okay, to come up with a model that is manageable. So you have a model of the system that you can analyze it. For example, you can represent this building with a bunch of, say, concentrated masses, and also beams or springs that connect the masses. That represents the building. So you will have a bunch of concentrated masses, as an example, connected with beams or maybe springs, and that represents the system. You have some boundary conditions. For example, you have supports. Okay. This is called an analytical model. So the first step results into an analytical model. An example is a finite element model. Finite element model. Okay, once you have developed that model, the next step is to derive the equations that govern the motion of the system. So the next step is the development of a mathematical model, which is nothing but a bunch of equations For example, you can have a mass matrix times the vector of the accelerations times the stiffness matrix times the vector of displacements, and this is equal to the force. This is the mathematical model. Okay. Once you have the mathematical model, which could be just a single equation or maybe hundreds or thousands of, or millions of equations, you have to solve these equations. And in practice, if you have a real life system, you cannot afford to solve it by hand or using your calculator. We have computer programs, such as programs for finite element analysis, that will actually solve these equations, and they will give you the behavior of the system. So you use a computer. So let's say that this box is a computer here, computer, and what you get is the displacement or the stress as a function of time. I'm sorry. So this is the time here, and this is the displacement. Using the displacement, you can find the stresses. Okay, you can find a bunch of displacements at different locations. Okay, now what do we do with these results? Mainly, we want to check if the system has acceptable behavior. So one way to do that is to calculate the stresses and see if the stresses are acceptable. If they are not acceptable, then you have to change the system. So you change the system, you change this model, you repeat the analysis until the performance becomes acceptable. Okay. Which of the steps? There are, as we see, 4 steps. The first one is to do a model. So you do some assumptions to do a model. Then this is a conceptual model or analytical model. The second one is the mathematical model, where you convert this sketch here into a bunch of equations. So this is the second step. And then the third step is the solution of the equations. Okay? Which of the steps is the most challenging? Well, typically it's this step. The step where you make a simplification, you start with something very complex, like a car, a building, and you replace it with something that is manageable, such as this bunch of rods connected with masses, and that you can solve. This is a kind of an art. There's no theory that you can use. So you got to have good judgment, to think a lot, to make sure that you have something that is accurate and at the same time simple enough so that you can model it. The other steps can be involved, but this one is the most critical step. If your model is not right, you are essentially solving the wrong problem, and you find the response of a system which actually is not the right system. So this is very tricky. Now, because this is mostly kind of intuition, art, the course is not going to focus on this step. So we'll start from this step, derive the equations, and then solve these equations. And once we solve these equations, we look at the response and see what we can tell about the system. Is it good, or how we can change it to improve the performance? Okay, with this, let's introduce some terminology. For example, we're talking about system, so we'll introduce some definitions. A system, we'll use the term system. In vibrations, a system is a combination of components that act together for some purpose. Okay, for example, you have a building, it's an assembly of components, and mainly we use it to protect people from the elements of nature. So, system is a combination of components acting together. So the objective, as we said earlier, is to learn how to model a system, learn how to model systems, and solve the models to predict the dynamic behavior. Okay, that's the objective. Now we're going to see some classifications of the system, starting from some simple systems and going to more complex systems. So, classification. Let's make a sketch here that will help us for classification. for this purpose. Okay. The left side, this represents linear systems. Okay? A linear system is a system whose equations involve only first powers of the unknown. So you don't have products of unknown quantities, or you don't have squares of the unknown quantity. So if x of t is an unknown, the equation may have x of t, may have the derivative of the second derivative or higher derivatives, but it doesn't have squares or nonlinear functions like the sine of the unknown, sine of x. So one classification of the universe of systems is into linear and nonlinear. Okay? It is much easier to work with linear systems than nonlinear systems. Nonlinear systems exhibit a very, sometimes unpredictable behavior. Solving the equations is very complicated, very time-consuming. Okay? Now, we can have systems with 1 degree of freedom. You can have systems with multi-degree of freedom, multiple degrees of freedom, multi-degree of freedom systems, or you can have continuous systems. So we have another edge here in the box that will construct, which represents the continuous systems. Okay. And we can connect them. Okay. Then we have multi-degree of freedom systems that are nonlinear. You have systems that are okay. So the back of this is for type of systems that are time invariant. So we'll make another part here. Okay. Okay. In the back of this, we have one plane that has to do, that represents the part of the universe of time invariant systems. Okay? A time invariant system is a system whose properties don't change in time. For example, the building, if you consider a short time period, you can assume that the properties don't change with time. Okay? So all these masses, the connections, these beams, they don't change in time. This is realistic if you consider either short time periods or something that the properties, a system whose properties don't change with time. Okay? If you think about a rocket is a time, as it operates, it's a system that is time variant. Why? Because the mass of the rocket as it burns fuel changes with time. Okay? So this back of this sketch here represents the time invariant systems, and in the front we have this side that represents time invariant systems. Systems whose properties change with time. Time invariant systems. Okay. In reality, where are we? If you want to represent exactly something, well, it is non-linear, okay? So you are on this side, it is continuous, okay? And it has, it is time variant, so this is where you are. If you want to represent a real system, it is time variant, it is non-linear, and it is continuous. So this is the reality. Okay? Most of the time, as we said, we want to do simplifications, so we may work with other type of systems, such as linear. You may consider that the systems are time invariant. In this course, we're going to consider linear systems. They can be single degree, multi-degree of freedom systems, or continuous, but they are time invariant. So what we'll focus on is linear systems. So this is the focus of this class. Single degree, multi-degree, and continuous systems that are linear, and the properties don't change with time, so it's time invariant. So this is the focus of this course, okay? The course focuses here. Course focus. Okay. Let's expand on the definition of a linear system. Linear system. The equation of motion has terms that are linear in terms of the unknown responses and the derivatives. So the equation of motion is linear with respect to the unknown response let's say x of t, and its derivatives. Okay, that's a linear system, the definition of a linear system. here is an example. 5 times the second derivative of the displacement plus, say, the first derivative, which you can consider it as the velocity, plus 2 times the displacement, equal to sine t. Okay, this is a linear system. It is linear because there are no second powers or nonlinear functions of x of t. So if we have here derivatives such as the second derivative or the first derivative, but you don't have any linear, nonlinear term. You don't have x squared, okay? Or you don't have sine of x of t. Now, someone may say, but sine of t is nonlinear. It's a nonlinear function of time. Yes, this is true, but this is a function of time. It's not a function of the unknown quantity. So what is important is the unknown quantity. You should have only first powers of the unknown quantity, the unknown response, and the derivatives. Okay? So this is a linear equation. We are going to consider or idealize a system as a box with one or multiple outputs. So if you have this equation, you can represent it as a box. Okay? This is the system. The input is the excitation. In this case, it's sine of t, the input. Sine of t, that's the input. And then the response is x of t, so that's the output. X of t. Okay? If a system is linear, the superposition principle holds. Okay? So linear systems superposition principle holds. The superposition principle says that if you apply simultaneously two excitations, two forces, the response would be the sum of the responses to the individual forces, to the two individual forces. For example, if in this equation you had sine of t plus cosine of t, then you could find x of t by finding the response to the sine, then separately work with the cosine, find the response, and then add the two responses. That's the superposition principle. So this principle says that the response produced by simultaneous applications of two different forcing functions or inputs is equal to the sum of the individual responses. Okay, so the response of the system to simultaneous application of two forces is equal to the sum of the responses to each individual force. Okay? This is a very useful property. For example, suppose that you were able to solve this equation and find x of t. What will happen if you wanted to find a response to 2 sine of t? So suppose that you had a response say that you had the response of this equation. So let's say that the response is x of t. You found it, okay? Then what would be the response to two times the sine? Well, you don't need to do any work, you just double this. So the response would be 2 times x of t. If you want to find the response to 3 times x of t, it will be 3 times x of t. If you have two different forces, sine, as we said, of t, and cosine of t, the sum of the two. Well, if you calculate individual responses to the sine and cosine, then the response to the total is the sum of the two responses. Okay? You understand that this is a very important property to know, because it can reduce a lot your effort. Once you have the response to a sine of t, you can find the response to any any function that is scale version of sine x of t. Okay? So it's a very good thing if and reduces the work a lot if the system that you deal with is linear. A nonlinear system has at least a term that is a nonlinear function of the unknown. So let's write a nonlinear equation. And we have to be careful about what is the important term. The important term to decide whether the function is linear or non-linear is actually the unknown. So non-linear system. Here is an example. That's an example of a nonlinear system. So you have a nonlinear function of the unknown x of t. Solving this equation is much harder. You may have to use a numerical method where you find step by step the response. That means You start from time 0, you find the response, then you continue by a small increment, and you continue and find the response for a lot of different points in time. So you march in time, and that is very time consuming. Okay, if you try to solve this in this equation on the computer, it takes quite a bit of time. Okay, the superposition principle doesn't hold. Superposition principle does not hold. Which means that if you find the response to sine of t, and you have to find the response to 2 sine of t, you cannot just double the response to sine of t. You have to solve the equation again from the beginning. Okay? Another term that we use for classifications of systems are time invariant systems. Well, a time invariant system changes, does not change with time, okay? So all the coefficients of this equation don't change with time. So coefficients of the equation do not change with time. Okay? If it does change with time, the system is time variant. Coefficients change with time. Of differential equation change with time. An example is this. So this coefficient that multiplies the displacement changes with time, so this is a time variant system. Okay? Again, if you consider a rocket, okay, say this is a rocket, it burns fuel, so the mass changes with time. So this is a time variant system. Okay? Mass changes with time. Okay, the last part of classification of problems And we're not going to classify now the system itself, but the excitation. An excitation can be static or dynamic. So, classification of excitations. The excitation can be static. Again, we represent the different types of systems with just some circles, or it can be dynamic. Dynamic means changes with time. Okay? Now, the excitation can be deterministic. Deterministic means that you know it, okay? This is deterministic. Anything that we have written so far, all the excitations are deterministic. But there are some excitations that are not deterministic. They are random. Okay? A random excitation is something that you can never predict, okay? An example is the wind speed, okay? This is T, this is wind speed. This is important in terms of the force that it exerts to a building, and this is something random. The speed changes with time, okay? And you cannot predict it. So this is the classification of excitations. 4 types, 4 combinations: static, dynamic, deterministic, and random. In this course, we're going to consider deterministic, dynamic. So this is the focus of this course. Okay?